How do you come up with a way to solve the biggest challenge of all? How do you find out if we are all alone in the universe? In life, we face multiple challenges. We face them at work, at school, or in our day-to-day lives. How do you tackle those problems? Do you usually try to address them in one go? Or do you tend to subdivide those problems into smaller problems? The South African Bishop Desmond Tutu, who lived between 1931 and 2021, and the receiver of the Nobel Peace Prize in 1984, wisely stated that there is only one way to eat an elephant, one bite at a time. This is just a way to say that the easiest way to tackle a challenge is understanding the nature of the challenge and partition it into smaller challenges. For those of you that are familiar with project management, for instance, projects are subdivided into stages or milestones. You usually don't progress to a given stage of a project until the previous milestones have been achieved. Hello, Dr. Alejo here, and in today's episode we will discuss how a visionary man tried to address the biggest challenge of all. How do we find out if we humans are alone in the universe? Everything started in 1959 when astronomers Cocconi and Morrison showed that interstellar communications could be achieved using radio waves. They went even further and suggested that radio waves could also be used for searching for extraterrestrial civilizations. As part of Project Ozma, Frank Drake had convinced a bunch of people that pointing radio telescopes to the stars and tuning them at the 1420 MHz frequency was a good idea to find intelligent aliens. In what has been referred to as the first modern attempt to detect interstellar transmissions, from April to July 1960, a search was run for 6 hours a day using the receiver on the 26-meter antenna of the National Radio Astronomy Observatory at Green Bank. Why the 1420 MHz frequency? SETI astronomers usually focus on what it is known as the water-hole frequency. Atoms and molecules can emit electromagnetic radiation like radio waves, light, X-rays, etc. whenever the energy state of the particles changes. Hydrogen atoms emit at 1420 MHz, which corresponds to a wavelength of 21 centimeters. Hydroxyl molecules, which are composed of one atom of hydrogen and one atom of oxygen, emit at 4 specific radio frequencies, ranging from 1612 MHz to 1720 MHz. When a hydrogen atom combines with a hydroxyl molecule, this results in a molecule of water, which is the most essential molecule for life as we know it. This frequency is also very relevant and characteristic of several astronomical events. Therefore, it is assumed to be a well-known frequency by any technological mature society. In 1961, the Green Bank Conference was organized with the objective of discussing strategies and ideas for the search for extraterrestrial intelligence. Notable attendees included a young Carl Sagan and Melvin Calvin, a Nobel Prize-winning biochemist. Frank Drake was in charge of leading and structuring the discussion. Or in other words, Dr. Drake was the guy that needed to set the agenda. The idea was to tackle the massive problem of estimating how many communicative extraterrestrial civilizations were out there in our own Milky Way galaxy. How do you solve a problem so big and difficult, especially when no one has ever done it before? This is where Bishop Desmond Tutu's famous saying becomes relevant. How do you eat an elephant? One bite at a time. In other words, if you want to solve a problem, a very good approach is to subdivide that problem into smaller tasks. And this is exactly what Frank Drake did. He wrote on the blackboard a simple mathematical expression, multiplying several variables to estimate the number of detectable extraterrestrial civilizations. The equation is really a probabilistic argument, which means that it gives an estimation rather than an actual number. A quick and probably silly example to illustrate what Frank Drake tried to achieve is the following. Imagine you want to calculate the probability of catching a specific bus route to the office between 7 and 8 a.m. Let's call that probability N, which represents the expected number of successful rides. Let's say that B represents the number of buses on our route that run between 7 and 8 a.m., which for our example we will set as 3, so b equal to 3. Let's also say that you are at the bus stop on time 80% of the time. Maybe some days you don't get up early or your kid makes a mess, etc. But 80% of the time you are on time. Let's call this variable OT for on time and assign the value of 0.8 to it. This corresponds to 80%. Now, you know for a fact that the bus service actually operates 90% of days. That is, no strikes, no cancellations. Let's call this variable A for availability and assign it the value of 0.9. Finally, let's consider the variable W for weather to indicate the chance that weather conditions don't cause major delays. Let's assume that 90% of the time we have good weather conditions, and therefore W is equal to 0.9. We then multiply all these variables together. N is equal to B times OT times A times W. And then we solve, so N is equal to 1.94, or almost 2 buses. This means that you can expect to be successful in catching at least 2 buses between 7 and 8 a.m. I hope that simple example helps you to understand the way how Frank Drake constructed his Drake equation. Frank Drake's approach was to select 7 variables or factors to organize his thoughts. These 7 factors are completely arbitrary, a point we will discuss in more detail later. Okay, so what were the variables used by Frank Drake? First, consider that we only have a sample of 1 when talking about the different planets in the universe that host life. That is, us here on Earth. Earth is the only planet that we know of that can sustain life. We haven't found any other planet in the solar system, our own galaxy, etc. Only us. It makes sense then to try to find another civilization similar to us. For example, we live on a planet, a rocky planet to be precise, where water can flow liquid on its surface, which means that we are at a given distance from our star, the Sun, that allows that to happen. So, life as we know it needs a star, a certain type of planet, and at a minimum needs to be a certain distance so it is not too cold, so water freezes, or not too hot, so water evaporates. This is known as the habitable zone of a star. Given that life as we know it needs a star, the first term in the Drake equation deals with, in average, how many stars are born in the Milky Way galaxy every year. This is called R asterisk. By the time Frank Drake formulated the Drake equation, this value wasn't that well known. Nowadays, though, the star formation rate for a region or the universe itself is a relatively known number. This number is given in terms of solar masses. For instance, it has been calculated that, on average, the Milky Way produces between 1 to 2 solar masses of stars per year. But life as we know it also needs a planet. The second term is the fraction of stars that host planets, or F sub p. As I mentioned in one of my previous episodes, the existence of other planets outside of the solar system wasn't something we had certainty of until 1992, when a planet was found orbiting the remnants of a dead star. This means that when Frank Drake proposed this term, he and nobody else were certain about the existence of exoplanets. But in 1995, astronomers detected the first planet orbiting around a sun-like star. And since then, astronomers have detected more than 6,000 planets. It has been estimated that, statistically speaking, every star has at least 1 planet. So effectively, this term is equal to the number of stars in the universe, or 100 billion. That is a 1 followed by 11 zeros. Now, out of all those 100 billion planets, how many of them can actually support life? The third term then is the average number of planets that can support life, and it is represented as N sub E. And here is where the habitable zone of a star comes in place. What is the problem? The habitable zone has many definitions. As I mentioned before, the most widely used is the one that indicates that a planet is in the habitable zone of a star if liquid water can exist on the surface of the planet. But according to that definition, in our solar system, Venus and Mars are also in the habitable zone of the Sun. But guess what? You don't find liquid water on Mars or Venus, at least not at present day. Strong evidence suggests, though, that water did indeed flow on Mars at some stage. The samples collected by Perseverance in September 2025 were collected in what it is believed to have been an ancient river valley. Now, out of all those planets that can support life or planets in the habitable zone of the star, what is the fraction of those planets on which life can actually appear? This term is F sub L. Providing the example of our solar system, only 3 planets are in the habitable zone of the Sun: Venus, Earth, and Mars. But only on Earth, life actually appeared. Note that this term only takes into account the definition of liquid water on the surface. But what we see in our solar system is that many of the moons of the gas giants, Jupiter, Saturn, Neptune, could actually sustain life due to the liquid oceans in the subsurface of the moons. This is not considered at all in the equation. Now, let's say that life indeed appears on a planet. The 5th term deals with the question of, out of the total number of planets where life appears, what is the fraction of those planets where intelligent life indeed develops? This intelligent life Drake refers to is human-level intelligent life. He is not considering intelligence such as the exhibited by elephants, octopus, dolphins, or whales, for instance. Okay, so now you have human-like intelligent life. Is this intelligence enough to allow them to manipulate electromagnetic waves, to make a video call, to communicate with a relative or friend on the other side of their home planet? The 6th term therefore deals with the fraction of intelligent life that can advertise their existence in space. For instance, on Earth, we have had many great civilizations. The Egyptians, ancient Greeks, and others were civilizations that reached a high point in science and maths, but they weren't able to come up with radio transmissions. Humans have only been sending long-distance messages for less than 200 years. And this connects to the final term in the Drake equation, the period that a civilization can communicate across space. How long will a civilization survive? Is a civilization's lifespan long enough to develop interstellar communications? Humans have been at the brink of self-destruction many times. Nuclear weapons, pandemic, even AI. Could wipe out humanity at any time, potentially erasing our existence in the universe and our possibility of being detected by another civilizations. The last term, L, deals with the longevity of a civilization. Okay, so these are all the 7 terms that Frank Drake used. The Drake equation is the multiplication of all these terms to find n, or the number of communicative civilizations in the Milky Way. By now, you may have noticed that out of all the 7 variables in the Drake equation, only the first 2, average rate of star formation every year and fraction of stars that host planets, are well known. The other 5 are completely unknown, and it is more than likely that they remain like that. And here is where the equation gets its bad reputation. A common criticism is also the arbitrarity of the parameters. There are so many variables that we could potentially include, but only those 7 were considered. Thousands of articles have been written trying to assign values to these 7 terms. Some of them use educated guesses, while others are just fully speculative. Due to these reasons, some scientists say that the Drake equation is useless. I don't agree with that statement. Just remember how the Drake equation was born. Its purpose was to promote a discussion around a challenge that was really hard to tackle, and not really trying to come up with a definitive number of extraterrestrial civilizations. Even after more than 60 years of being formulated, we're still talking about the concepts that it introduced, such as exoplanets, habitable zones, and the longevity of a civilization, just to cite some examples. I do agree on something though. People have abused the equation to demonstrate some hypotheses, and this is where the problem really lies. 2 of my favorite YouTube channels have explored in detail the pros and cons of the equation. I will leave the links in the description if you want to dig deeper. One thing that is clear to me is that the legacy of Frank Drake is still alive. Unfortunately, Frank Drake passed away in September 2022 at an age of 92 years. But his equation has inspired and continues to inspire many scientists and invited members of the general public to talk about the possibility of extraterrestrial civilizations. But maybe the greatest achievement of the Drake equation is to highlight how little we know about the possibility of life in the universe and what factors make possible the existence of such a life. As Jill Tarter elegantly put it, the Drake equation is just a way of organizing our ignorance. If you got up to this point, please give this video a like, and if you don't want to miss the next episodes, subscribe to the channel. I will be very interested to hear your thoughts about the usefulness and overall value of the Drake equation. So please share your opinion in the comment section. Also, as you can see, I'm experimenting with different backgrounds, different lights, different microphones, etc. I'm also curious to know your opinion on these new settings. Bye for now, and remember, the truth is out there.